Good morning, everybody. Um, I hope you can hear me.
Yes.
Yes.
Did you start studying something? Ah, not yet, huh? Uh, okay, up to now we have been very exotic, talking about philosophy, epistemological aspects, and so on. And from now we shall become more concrete, go more in the details of the processes, what we may model or we may describe with our models. And in order to do that, today we shall start with an overview of the processes, physical, chemical, biological processes that may be modeled by the approach we propose in our class. In order to do so, we shall introduce the first composition of the ecospheres, so of the description of the uh, situation on our planet, on the surface of our planet, in terms of different ecospheres. Uh, Different spheres, meaning that we subdivide in terms of space, time, and processes the various interactions that are happening between the different ecospheres we may employ to subdivide the ecosystem that is populating the surface of our planet. The four spheres that classically we employ to describe interactions between the different elements of the ecosystem are sky, land, surface, and aquifer. Surface water systems and aquifer. In particular, let's give a look at what happens in the interaction between sky and land. First of all, we shall note that given that water, as we have said, it is the media that transports from one side nutrients and elements necessary for to sustain life, and from the other side transport waste product of the metabolic processes or the living processes. We shall first of all give a look at the cycle of water, and very trivially, I imagine you already have an idea of it, but let's start in order to introduce the concepts and the terms. We shall start by observing that the cycle of water is closed on the surface of the planet in this way. First of all, water is accumulated in the atmosphere, in clouds. From the atmosphere, water is transferred through rain or snow to the land surface or to the surface of the planet. And so once water reaches the surface of the planet, we may identify different pathways through which water moves or vehiculates on the surface of the planet, in particular, surface pathways like overland flow and runoff that move water from the falling point on the top of a mountain down to the receiving water bodies, that is rivers, seas, and lakes. And we may also identify groundwater flows that are very relevant because, as you can imagine, as environmental engineer, groundwater is another important way through which water moves from the surface, from the falling point to the receiving bodies, in particular rivers, lakes, or oceans or seas. From the water bodies on the surface of the planet, so from rivers, oceans, and lakes, water is transferred back to the atmosphere through processes like evaporation, transpiration. So water falls on surface of the mountains, a part of this water through overland flow, runoff, surface runoff, those reaches the receiving water bodies, another part through groundwater flows that are quite complicated to model, in particular because groundwater flows have very high times, requires a lot of time compared to surface or overland flow. It requires a lot of time to move water from the groundwater through the groundwater pathway to the receiving water bodies. This makes the fact that we may have effects of, for example, pollution events or loads appearing on the surface of the planet, on the surface of land, that it is manifested on the receiving water bodies even after very long time. While we are talking about days, months, maybe years for following the water that moves through surface, water flows, water that moves through groundwater flows may take even decades or centuries or several centuries. This means that we may have a pollution event in some place on the surface that impact some places on the surface of the planet, and then we may say the effect of this pollution event that happens in the surface water bodies even some decades or centuries after the event itself. As I told you, water is a very important element because it is a very particular chemical compost, or particular molecule that has the ability of dissolving and transporting most or maybe all of the chemical elements that may be impacting on the surface of the planet. Typically, the spheres of the geochemical physical model describing the Earth are four: the atmosphere, the hydrosphere, and lithosphere, and biosphere. By this, we mean that the area near the surface of the planet can be divided essentially into four connected geospheres, four interconnected geospheres that are all interacting each other. Please note that this subdivision is not sharp subdivision between the ecospheres, because, for example, atmosphere and hydrosphere, just to give you an example, are permeating one each other. This means that the atmosphere is in the air, but water may be found in the atmosphere in the form of vapor, or clouds, or things like that. But also we may find water, so a portion of the hydrosphere that is somehow mixed or interconnected with the lithosphere, like, for example, humidity on the surface of the planet. Of course, the sphere that is most new for the environmental engineer is the biosphere. The biosphere is where all living process happens. And so we will spend the second part of our class in discussing processes happening in the biosphere, and we will give some examples how to model these processes. The atmosphere is the body of air which surrounds our planet. Most of our atmosphere, it is located close to the Earth's surface, where it is most dense, you may recall, but the atmosphere density depends from the high height, so from the distance from the surface of the planet. The air of our planet is 78% nitrogen, and you may this tells you that the atmosphere is a sink or a reservoir for nitrogen, and just under 21% is oxygen into the atmosphere. So the two main components of the atmosphere are nitrogen, or its large majority, and oxygen. The small amount remaining is composed of carbon dioxide and other gases. Please note that these figures we have already cited, for example, a 21% oxygen concentration is a very particular value of the concentration, but it is exactly the value of concentration that allows oxygen respiration to take place, and that impede or make impossible the process of cell combustion that would happen if the concentration of oxygen in the atmosphere would be even slightly larger than the 21%. The hydrosphere is composed of all of the water on or near the Earth. These include, of course, ocean, rivers, lakes, and groundwater. That is one largest part of our planet that contains water, and even moisture in the air. As I told you, it may be seen as part of the hydrosphere, of the sphere describing the processes of water. 97% of Earth water is in the oceans. So just to tell you that the oceans are a large reservoir of water. 3% is fresh water, and three quarter of this fresh water is solid and exists in ice sheets on glaciers or on the polar areas. The lithosphere is the solid rocky crust covering the entire planet. It is composed by inorganic and various components and various minerals, so maybe inorganic and organic. It covers the entire surface of the Earth from the top of the Mount Everest, that is the highest point in the surface of the planet, down to the bottom of the Mariana Trench, that is the lowest part of our surface, on the surface of our planet. The biosphere finally includes all living organisms like plants, animals, and one-celled organisms are all part of these living processes. Most of the planet life is found from 3 meters below the ground to 30 meters above it, and in the top 200 meters in the ocean and sea. So this is to say that most of the living forms are found in this portion of the space around the surface of our planet. But please note that we may find some very rare living objects that may be found even in the deepest part of the oceans, like for example in the sulfuric jets in the bottom of the seas, in which we may also be seeing, we may also observe living objects that have developed very peculiar biotechnologies to convert or to extract energy from molecules, in particular, in the case of non-oxygen respiration, so anoxic transformations, we may find that there are some bacterial species that have found biotechnologies to obtain energy from our sources as well. Okay. We have said that we shall concentrate during this lecture on a very peculiar molecule that is called hydrogen oxide, or hydrogen or oxygen dihydrogen oxide, the so-called water. Water molecule is very particular for several reasons. I will try now to give you some ideas why this molecule is particular. It is important to note that the peculiarities of this molecule are essential to the installation of living processes as we observe nowadays on the surface of the planet. So hydrogen oxide or water is made up of a large molecule of oxygen that is linked with two very strong covalent bonds, the so-called hydrogen bonds with two atoms of hydrogen. Um, this is a very dipolar molecule. Water is a very dipolar molecule. We may describe the dipole by observing that the oxygen contains the largest part of a negative charge of a molecule, while the hydrogen contains the largest part of the positive charges of a molecule. This makes the molecule very dipolar, and this is one of the principal causes of the chemical characteristic or the ability of this molecule to act as a solvent and to transport our chemical elements, our large chemical molecules. In particular, for environmental engineers, we think about toxicants or pollutants through the various spheres but with which we have subdivided the surface of the planet. It is striking, impressive to see that this molecule, large dipole with a large oxygen and two small hydrogen, has some, let's say, topological characteristics or topological proportion that are somehow very impressive. Like, for example, we find this kind of proportion in several contexts. It's a little bit like what we call the gold section, a number that somehow regulates some of the geometries on the planet. In particular, I find striking the fact that this very important molecule resembles a little bit a Mickey Mouse proportions, in which we have a large face with two small ears. And this recalls probably the creator that Disney introduced in the 50s of the 20th century, that is Mickey Mouse. What are the anomalies of this very strange or peculiar chemical compound? First of all, water has a high melting and boiling temperature. This means that in order to see water changing phase from its solid to liquid and from the solid to gaseous form, we we expect that this happens in a quite high range of temperature. Water has a high specific heat. This means that it is a very strong buffer for thermal transfers. This means that energy transferred through heat is maybe largely accumulated in water. It is the substance that exists in more stable and metastable states, going from crystalline to amorphous states. So we see water in form of ice, crystalline, solid, or in the form of vapor, or in the form also of other amorphous conditions. Remember that water, it is an excellent solvent, probably not the most solving element, but very excellent, very strong solvent in the sense that water may solve, or we may find dissolved in water a very large number of substances or a very large number of big molecules or big chemical compounds. One of the first anomalies that we shall recognize in the structure and the topology of the hydrogen oxide, for example, are linked to the dimensions of the atoms making up hydrogen oxide. This ends up with a distance of less 1 angstrom, or less of 1 angstrom on the center of the oxygen and the hydrogen. So the hydrogen are almost 1 angstrom distant from the center of the oxygens. Angstrom, I recall you, is 10 to minus 10 meter. So it's a very small distance compared to the macroscopic world, but of course it is quite a large distance compared to the microscopic conditions. And the other relevant aspect of this molecule that you should remember is that the angle between the two hydrogen atoms linked with the covalent bonds, sorry, the hydrogen bonds to the oxygen atom display an angle of 104.45 degrees. It is this structure that makes up, for example, that solid water, it is less dense than liquid water. And this is a peculiar characteristic because most of the other elements, the solid phase is denser than the liquid phase. In contrast, for water, the solid phase is less dense than the liquid phase, and as a macroscopic effect of this condition, we see that solid water floats on liquid water. So we see that ices are floating on liquids. These, for example, peculiar characteristics of these molecules, for example, makes the fact that, for example, under ice sheets, we have a kind of controlled temperature conditions. So under ice sheets, the temperature of water under ice sheets is larger than 0 degrees, of course, because at 0 degrees water becomes solid. And this makes possible some life forms also to colonize the water bodies under ice sheets. So we may find living objects also under the ices. I try to summarize the anomalies of water in these collective curves. In particular, let's focus on the density, as we were talking about before, starting from the 0 degrees, moving from the 0 degrees point in which the density is higher. In all other conditions, the density of water is lower. Actually, this is not exactly 0, but you may recall that the maximum point of density for water is 4 Celsius degrees. This means that this maximum 4 Celsius degrees, and as I was telling you, if we have ice floating on water, on liquid water, so solid water floating on liquid water, the liquid water beneath the solid is at 4 Celsius degrees. This is why in some extremal conditions, we may find living forms also under ice sheets. Several other peculiarities, for example, are evident if we look at the specific heat of water. As I told you, specific heat is very high, which means that water can absorb a lot of thermal energy. So it is a good buffer for thermal energy. And in particular, specific heat of water has a minimum between 30 and 40 degrees. So going away from this minimum, the specific heat grows and away from the 30, 40 Celsius degree minimum, um, water may absorb in a significant quantity heat or thermal energies. How do we find water in the biosphere? Water is of major importance to all living things. In some organisms, up to 90% of their body weight comes from water. In particular, for us humans, up to 60% of the human body is water. The brain is composed of 70% water, and the lungs are nearly 90% water. Um, I recall you that water is an important solvent, and the fact that we have a lot of water in our lungs means that we may observe an important passage of oxygen from the air into the liquid that is making up the volume of the lungs. In particular, about 83% of our blood is water, which helps digest our food and transport waste. They told you, water, a very important solvent, may transport nutrients from one side and waste on the other side. And moreover, the fact that the 60% of water of a human body is water, this also helps due to the very high heat capacity of this molecule, um, may help in controlling the body temperature, in keeping constant the body temperature. And as we know, this is an essential aspect, especially for mammals. Each day, humans must replace 2.4 liters of water, some through drinking, and the rest is taken by the body from the foods eaten. So 2.4 liters of water. This gives you some indication on why it is very important that you drink daily a lot of water. At least 1 or 1.5 liters is the minimum quantity of water needed for a mammal like we are in order to maintain his condition in a steady state condition, or if you want, in an homeostatic condition in which the chemical physical conditions are maintained quite stable. Then another important class of substances that are of special interest for environmental engineers, like for example, heavy metals that are toxic substances. Heavy metals are chemical elements that have the following characteristic: densities exceeding 5 grams per cubic centimeter. They behave essentially as cations, so positive ions. They have a remarkable ability to form complexes, and the low solubility of their hydrates also is a peculiar characteristic of these heavy metals. Heavy metals have very or display very different oxidation states depending on pH and EH condition or alkalinity condition, and they have also a great chemical affinity for sulfides in which they tend to concentrate. So all these chemical characteristics of heavy metals make these toxic substances persistent and ubiquitous on all the four spheres, and in particular on the biosphere that is made up of, as we said, it is strongly interconnected with the hydrosphere and in the biosphere, in which we may find several quite complex molecules like sulfides, and various complexes. The heavy metals, by definition, pertains to the so-called transition elements in groups 6, 7, 8, 1, 2b's of the table of the elements of Mendeleev, but also in groups 3 and 4. So the heavy metals This is the table of Mendeleev, of the elements of Mendeleev. The heavy metals essentially are found in these groups, the ones that are bounded by the dashed red line. But of course, we have also some elements in the confining groups, like for example, aluminum or gallium, or in some cases manganese or calcium and so on, but may also behave as heavy metals or may display a behavior that is similar to that typical of the heavy metals that are chromium, manganese, iron, cobalt, nickel, copper, zinc, and so on. So the ones including this rectangle that is bounded by this red dashed line. Heavy metals are important toxicants or molecules to be followed because they tend to be or to accumulate in soil, but soils or topsoils act as a filters for these toxicants. And the basic parameters that govern the ability of soils to store or to trap heavy metals are pH condition, redox potential, content of organic matter, cation exchange capacity, and so on. In particular, the content of organic matter is a key characteristic of the soil, but gives you hinders or give you guidances in order to understand how large is the capacity of a particular soil to act as a filter for heavy metal or for these toxic substances, heavy metal or other toxic substances behaving similarly to heavy metal. Okay, this is a table refers to Italian law. It is a ministerial decree of 1999, number 47.1. These are the regulations established. These are the regulations that is establishing criteria, procedures, and arrangements for the securing and restoration of polluted sites. So for land reclamation and for the control of the capacity of trapping toxic substances from the soil. In particular, we may say that the limit value established by this decree, 1998-471, that has been included and amended into the 152 law. The limits, for example, are differentiated in terms of use of the area, in particular the limits for green areas, public or private, are much more stringent than the limits imposed for our sites of commercial or industrial interest, of course. These are some figures for the different elements that tells you what are the acceptable concentration. Of course, if you look at this list, cadmium, chromium, copper, nickel, lead, and zinc, you see that cadmium is considered the most toxic one, meaning that only 0.6 milligram per kilogram of soil is allowed by law, while, for example, in this context, zinc is considered the less dangerous one, allowing by law 110 milligrams per kilogram of soil as a concentration into the topsoil. Land reclamation is a very important point of this decree that concerns the choice of remediation techniques. In particular, Article 4.4 of the decree obliges of reclamation and environmental restoration. It is stated that the intervention for remediation and environmental restoration of a polluted site should be give priority to the use of techniques that promote the reduction of the handling in situ treatment and reuse of the soil, subsoil, and landfill materials subject to remediation. Point is here that the idea is that we have to promote reduction of the handling and in situ treatment of these topsoils. I think in the class by Professor Raga, remediation of contaminated soil, you should have seen in very large, in very deeper details these aspects. So let's now go to the very core of the subject of this lecture. Let's talk about a topic what I call the equilibrium between spheres. We said that toxic substances are present in various forms in the different spheres, the lithosphere, hydrosphere, atmosphere, biosphere. And when the environmental engineer thinks or looks at toxic substances, he has in mind heavy metals or persistent organic pollutants or polycyclic aromatic hydrocarbons or more complex molecules of human origin like pesticides or nutrients that may be considered pollutant as well, or other kinds of drugs. Various spheres can be in equilibrium or there may be some kind of dynamic exchange phenomenon. So several of these dynamic exchange phenomena that describe interaction between the spheres may be included into your ecological model of the site that you're studying. The exchanges between the spheres are usually described by relations between the equilibrium concentrations. The transfer of a compound takes place until the equilibrium concentration are reached. So the end point of a transfer between the spheres are equilibrium concentrations. The rate of a transfer is generally proportional to the distance from the equilibrium, so how much we are far from the equilibrium concentration, and depends on the diffusion coefficients of the compound, so it depends on specific characteristic of the compounds you are studying, and on the resistance at the interface between the spheres. So of the characteristics of, in physics we call it la sezione d'Urto, heat, heat section. The sezione d'Urto is an indicator of how strong is the interaction between the two elements or between the two sides, and this is described in terms of resistance at this interface. The resistance on its turn depends essentially on the diffusion coefficient, but depends on its turn on the temperature on the area exposed to the atmosphere or to the liquid volume, and on the rate of the flow. So the resistance is a parameter describing how easily a particular substance, according to its characteristics, is moved from one sphere to the other one, according to the specific characteristics of the spheres we are focusing on. A first example of interaction between spheres is the interaction between hydrosphere atmospheres. Interaction between hydrosphere and atmosphere is described by very well-known Henry Laws. Henry Laws tells that the concentration in the liquid phase is equal to a partial pressure in the gaseous phase of the substance divided by the Henry constant. So here we have a first model of interaction between hydrosphere and atmosphere, in which we have two characteristics, two parameters describing the condition in the two spheres. One is the concentration in the liquid phase, and the other one is the partial pressure in the gaseous phase. And this interaction is regulated by a constant, the so-called Henry constant, that is a characteristic typical of a substance. Different substances have display different Henry constants. By trivially employing the law of ideal gases, law that tells us that pressures times volume is equal to the number of moles multiply R multiply with temperature, we may reverse or substitute pressures in terms of concentration, and then we may recast Yanis law in terms of concentration in air and concentration in the liquid phase through Henry constant characteristics of a particular toxic substance divided by the condition at which this transfer takes place, that is essentially with temperature. But I recall you, we said that the diffusion coefficient depends strongly on the temperature. But the diffusion coefficient depends also strongly on the area of the interface between the two spheres. In particular, a first explicit model of transfer between the hydrosphere and the atmosphere is the Whitman's two-fin theory, in which we introduce, subdivide the space in terms of liquid phase and gaseous phase, the liquid bulk and the gaseous bulk, and then at the interface with black line, we may consider two small films, so gaseous films and the liquid films. So the interaction or the exchange happens exactly in this portion of the space that characterizes the interface. How can we describe this process? I give you a very trivial way of extracting a model of interaction between these phases. We start with Whitman's two-fin theory. We start by computing the flow per unit areas. So we define the JL, that is the flow through the liquid film, that is equal to a constant of equilibrium KL times the difference in concentrations. Please note that I am resuming all things that we have said here. The rate generally is proportional to the distance from equilibrium, or if you want, difference in concentration, and depends on the diffusion coefficient and so on. So formally, we may write that the flow in the liquid film is depends on the concentration at the interface minus the concentration in the liquid bulk, and this is mediated by an equilibrium constant KL. Analogously, we may define the flow in the gaseous phase that is equal to the difference between the two partial pressure in the gaseous phase and partial pressures in the interface. So we are subdividing the problem from bulks, parts, and what is going on around the interface by considering films. We know by the law of ideal gases that concentration is related to pressures by this relationship. Sorry, we know by Henry's law, sorry, that the concentration and pressures at the interface are linked through the Henry coefficient. So these concentration are linked depending on a parameter, but depends on the characteristic of a substance in equilibrium conditions, or if you want, in steady state condition, in which the flow in the gaseous phase is equal to the flow in the liquid phase. So we said that in steady state condition, this flow is J. Then we may simply explicitate this J by employing this definition, and we obtain that the flow is equal to the difference between the partial pressure in the gaseous phase divided by the Henry constant minus the concentration in the liquid phase. This is a kind of driving force or potential difference, a force that is pushing the transfer from the two phases. I recall you diffusion coefficient and the resistance at the interface. The resistance at the interface and the diffusion coefficient depends on the temperature. And so the temperature appears also in this definition here. You may recall by your physics classes the law of Ohm that states that um, the current or the flow is equal to the potential difference times a resistance. In this case, we may consider what appears here to the denominator as a resistance. So we may write that the flow of substance J is equal to a resistance that is made up of two terms, the first one and the second one, multiplied by a potential difference or a force that is pushing the flow through this interface. It is noticeable that this resistance is formally similar to a series resistor. Sorry, excuse me. I had to drink a little bit. In this case, this series resistor takes into account the first part, what is the resistance in the liquid phase, and the second part, what is the resistance in the gaseous phase. So by this schematization of the process, we end up with a model that describes how material may flow from the hydrosphere to the atmosphere by employing simply Henry's law and the law of Ohm in terms of resistance. In particular, for different compounds, this graph shows you how the different compounds are behaving depending on their value of the Henry constant. And in general, we may notice that in terms of percentage resistance in the liquid phase, so how much the liquid phase is controlling the transfer, we would say that for large Henry constant elements or large Henry constant compounds, we have a liquid control behavior. This means that the important part of the resistance is found in the liquid phase, while for small values of the Henry constant compounds, the control is exerted in the gaseous phase. So we talk about this in terms of gas control or liquid control flows. This is very important when you deal with toxic elements. For example, here you have, I have tried to categorize different substances, for example, dieldrin, lindane, that are toxicants. These are pesticides, essentially, or DDT, or we go up to polycyclic hydrocarbons, polycyclic aromatic hydrocarbons, methane, octane, and so on, but also some other elements like gaseous nitrogen and oxygen may be found in this table. More interestingly, you may notice that this kind of sigmoidal behavior or sigmoidal dependence of the resistance in the liquid phase with the Henry constant is different for different water bodies. In particular, for the Great Lakes, we expect that the passage between the resistance in the liquid phase and resistance in the gaseous phase is reached more quickly in terms of Henry constants, while for small sheltered lakes, the resistance, the maximum resistance in the liquid phase is reached more slowly. What does this mean? Great Lakes are lakes that are subject to wind, fetch, waves, surface, and so on, surface processes of radiation, while small sheltered lakes are small lakes in which the wind does not have a large surface to flow, to blow on, and to make interaction, to make stronger the interaction between the atmosphere and the liquid. And another aspect is that of surface of the interface. Great lakes are lakes for which water bodies for which the surface between the liquid phase and the atmosphere is large, while small lakes, the surface of the interface, of course, by definition, is smaller. And so in this case, for small lakes, we are in a condition in which we quickly reach a liquid control phase. Okay, I hope this gives you some hints on how to read this type of graphs, because this is the type of graphs gathering a lot of information concerning several classes of toxicant, putting them all together and allowing the environmental engineer to compare the dynamicity of various toxic substances, for example, in passing from the atmosphere to the hydrosphere. In particular, we may say a particular case of this interaction, this process of volatilization, so transfer from the liquid phase to the gaseous phase. So this is the transfer from of a substance that is dissolving in liquid to a substance that is dissolving in gaseous phase. The model, as you may recall, starting from here, you employ this kind of formalization. The model is one. So volume times the variation in time of concentration of the liquid phase is equal to a rate, a constant representing the rate of exchange or transfer coefficient, multiplied another number figure that represent the area of the interface, in particular, if you were thinking lakes, that may be the water surface of a lake, and this resistance is multiplied by a potential difference of potential transfer, like in the case of Ohm laws, in which we have a difference between the concentration in the gaseous phase minus the concentration in the liquid phase at the interface. So we are still applying the Whitman two-film theories. For toxic substances in general, we know that the partial pressure is almost zero. The partial pressure in the gaseous form is almost zero. This means that most toxic substances, we may find them in the liquid phase, dissolved in water. I recall you that water is the greatest solvent in the world. In this case, you simplify this relationship with some very trivial algebraic calculation. You may compute the speed of transfer, the so-called volatilization speed of a particular substance. In this case, the volatilization speed depends by the equilibrium constant in the liquid phase at the interface, time the Henry constant. So this volatilization speed depends on the interface and on the characteristic of a substance through the Henry constant, but also depends on the ratio between the equilibrium concentration in the liquid and in the gaseous phase at the film. In general, we may express these equilibrium concentrations as function of diffusion coefficients. In this case, we have written that the equilibrium concentration in the liquid phase is equal to the diffusion coefficient in the liquid divided by the density of the substance in the liquid phase, and so similarly for the constant of concentration in the gaseous phase. I recall you again. The rate in this case the volatilization speed, is proportional to the distance from equilibrium. Differences in concentration or in partial pressure is through the Henry's law and depends on the diffusion coefficient, so the characteristic of the interface, but maybe summarized by the surface or by the fact that we are in a sheltered lake, so a place in which wind cannot mix up or move water, so cannot interfere with the transfer between the two phases. In general, we may find that the equilibrium constant in the liquid phase may be made somehow dependent to the equilibrium constant in the liquid phase of oxygen by this ratio, 32 divided by the molar weight of a particular substance that you're looking at. So you make, for a particular substance, you make evaluate the equilibrium constant in the liquid phase through equilibrium constant in the liquid phase of oxygen, normalized by a parameter that depends on the mass of a substance that you're studying. For the gaseous phase as well, we have a kind of dependence on the mass of the substance that we are studying, but also in this case for the gaseous phase equilibrium, you have also to include a factor, for example, representing the effect of wind. In this case, this specific law links the equilibrium constant in the gaseous phase to the molar mass of a particular substance through the speed of the wind on the surface of water body. Again, is another way of characterizing the effect of interfaces. Again, we may collect some information concerning different substances, and different substances behave differently according to their Henry constant, what is a chemical characteristic of the substance, but also according to their molar weight, what is again a chemical characteristic of a substance. In this case, we may find this type of graphs in which we may locate, we may calculate or have estimation of Henry constant values in terms of logarithm of Henry constant values in terms of soluble and insoluble substances. So for soluble substances, we will have very low value of log Henry constant, while for insoluble substance, we will have very high value of log Henry constant. And in terms of volatilization rate, we have different volatilization rates that tend to a maximum volatilization rate in different ways, depending on the molar weight of the substance that you are studying. So we fix the speed of the wind, let's say 5 meters per second. And in this case, by this kind of graphs, you may have an estimation of how much may be the volatilization rate for a particular substance whose Henry constant is represented on this horizontal axis. Again, I've tried to classify different toxicants or different toxic substances in terms of their Henry constant in order to show how different substances may have different volatilization rates. And in particular, we may notice here that phthalates and esters that are found more or less here are essentially soluble, while other substances like ethers or halogenated aliphatics or PCBs and so on are more insoluble substances. That means that you will find with substances mainly in the liquid phase. Okay, concerning the interaction between lithosphere and hydrosphere, and I'm quickly going to the conclusion of the lecture. We essentially talk about the process of adsorption that you have already seen here and there. We may have three models. We may employ three models for the absorption process, and we build these models starting by an assumption of isothermal condition. So we have various way of representing this interaction. Absorption is passing, I recall you, from a liquid sphere, from a liquid hydrosphere to a solid sphere, so to a lithosphere. With two isotherms are found in Langmuir, and the most general model is called the partition coefficient model. But we will have much more time to go into details into these processes next week. By now, I stop here. I hope you have been able to follow, and I stop, close the class, and we'll go back on this.